So we got to the place where, but we haven't designed the sampling design yet, okay, or the actual assignment of treatments. So the nice thing about this is it's going to feel, assigning treatments randomly is very, very similar to randomly selecting, okay? So if I have to essentially pick 30 people of my 90 volunteers to receive the low-fat diet, I'm going to start by assign each volunteer a number. Between 1 and 90. Is this feeling familiar? Okay, then what am I going to do? Use a random number generator, since we're whispering, to get $30 unique numbers. Those volunteers follow the low-fat diet. I don't know why I put a space there. Do you guys see how this randomly assigns them? Cool? Okay. Have we assigned all the treatments yet? Okay. Use a random number generator to get 30 more unique numbers. It's one of the few times where you can use the phrase more unique. These volunteers get a low-carb diet. Do I need to generate 30 more numbers? No, I only got 30. The remaining volunteers get the pamphlet. Do you guys get how, like, are we good in terms of, this is by far the easiest way where you can just assign treatments, but you're doing it by chance. Okay. Now, yesterday we talked about, like, we have these variables we can control for, right? But we also had variables that we couldn't control for. So what we're going to talk about next are just different sampling or different experimental designs, and experimental designs are all about how we assign these treatments, okay? So if I follow just this right now, I have done everything fine, okay? It is very, very likely, as long as I'm randomly assigning, that the really tall people are going to get evenly distributed amongst the groups. Is it guaranteed? No. But there's no reason to believe that they wouldn't. Right? I'm not systematically putting tall people in one group. Okay? Everybody good? All right. So this design, the way we just did this, is called a completely randomized design. Okay? And in a completely randomized design, we use chance to assign groups. To entire study. Okay? Now, what we might want to do, because we didn't have that guarantee, we might say, hey, no. I want to put all the, I'm really worried because, like, you guys, if you guys try to lose weight, it's a very different thing than for somebody my age to try to lose weight. Are you with me? Like, your metabolisms are completely different. Okay? So maybe I want to say, hey, I want to make sure that the ages of each treatment group is about the same, right? So, like, old people, all three groups need to have about the same amount of old people and the same amount of young people and the same amount of middle age or whatever. You guys see what I'm saying here? Okay, so sometimes we have a randomized block design, and for a randomized block, you divide into blocks. Blocks being something that they have something in common. Okay? Blocks and strata are really, really close to each other. Okay? Now, divide into blocks, and then what you do is you assign the treatments within each block. So, you guys, if all three groups have the same amount of old people, the groups are still going to end up starting off on equal footing. What we wouldn't want is a lot of old people in the low-fat group and a lot of young people in the low-carb group, because then that's going to make the low-carb group lose weight faster, right? It's going to look like it's the low-carb diet that made people lose weight, and rather it's the fact that it was young people in that group. And then age would be confounding. Everybody good? So, yes, age and height and all of those things are potential confounding variables, but they're not confounding if they are evenly distributed among the groups. The groups are then still starting off on an even playing field. You guys see what I'm saying there? Okay? All right. Now, there's one last thing, experimental design. It is called a matched pairs design. And in a matched pairs design, there's kind of two things. A subject receives both treatments. Okay. Another example of a matched pairs design is a twin study. So basically you are creating where you can compare individuals to each other. Everybody good? Okay. So let's take this idea that I want to decide, does listening to music actually help you focus? Okay? Now, if I wanted to do a completely randomized design, so what are some things in general, no matter what, that we would want to control for? How am I going to measure how you focus? Let's start there. The amount of work that gets done in something? Okay? So my response variable is, I'm going to do this differently. I'm going to say time to complete a task. Is that cool? And so we would want to design a task that it's not the difficulty of the task that is a variable. So we maybe like everybody has the same task. Yeah? Okay. But it might be something like coloring or something like that, right? It wouldn't be something where the task could be, like if the task is difficult, it could take you long because the task is difficult, not because you're less focused, right? So we'd have to kind of think through that. Okay? What are some things we would want to control for? We'd want the task to be easy. What else?
Age.
Well, we can't control for age.
What music you listen to?
The type of music I think would be important. What else?
The setting they're in.
Yeah. For instance, is he talking? I can't focus. Like I have to put in noise canceling headphones if I'm trying to like get stuff done while he's teaching, because it's so loud. Yeah. Okay. Certainly, we would want to be in the same setting. Maybe away from the window. Because I don't know about you guys, but I used to have my desk facing this way, so I was like, I could look out the window and not, and you notice it doesn't face that way anymore because I couldn't get anything done. So I would just stare out the window over and over again. Okay? All right. So, who should my subjects be? Should I just use my students? Why couldn't I just use my students?
Would overrepresent upperclassmen.
One, I only represent upperclassmen. Not only do I only represent upperclassmen, every single one of my courses is a college level course. Either AP is considered college level or, right? So certainly I would maybe do a random sample of students to do this. Okay. All right, so let's say I have this random sample of students, okay? I'm going to start there, right? And then I'm going to randomly assign music, no music. In this particular case, is there a control group? Not really, because my treatments are music and no music, right? Could I create a control group? I'd argue that I could do one thing that might be considered a control group. Well, I was going to go with a white noise machine. So is it the music that keeps people focused, or is it the drowning out of other noises? Does that make sense? Also, silence would be virtually impossible to create in a school.
Saying like noise canceling headphones or something. Because with no music, you still have the outside like rain, wind.
Do we get the basic idea here? Okay. Now, some other things that we might want to consider is, say, age, right? So what if I took the 9th graders and I assigned my treatments? And then I took 10th graders. And then I had 11th now, because I want to make sure this is clear, how many treatment groups do I have now? I have 3 treatment groups. The music group, what can I say about the music group? I know it has in the 9th, 10th, 11th, and 12th graders in it. Do you guys see what I'm saying here? Like, my treatment groups are still the groups. Or within each treatment, what I've done is, like, when we do this blocking, it ensures that those other confounding variables are equally present in all the groups. Everybody good? So if I do it this way, are my groups starting off on an even playing field? That's the goal, always, is that your groups start off looking about the same. What we want is that the only difference between the groups is the treatments themselves. I can't say that enough times. Okay? Whenever we're doing an experiment, the whole purpose of all of the prep of an experiment is to make the groups as close to each other as possible before the treatments. Okay? Because if they start off on the same ground before the treatments, you apply the treatments and then they're not on the same ground, then we can say the treatments did it. Okay? But if we don't have them on the same ground before and they're different from each other, we don't know if that difference was because of the treatments or not. Everybody good? Yeah.
Is there like a point when we're starting an experiment that we can kind of decide we've gotten as close as we're going to get to
Yeah.
people?
I mean, yeah, otherwise there would never be an experiment because no matter what, it's not going to be perfect. Everybody good? Okay. There's one more type of that match pairs that I would like to. All right. And that is a match pairs design. So here's what would happen if I wanted to do a match pairs design. Okay? I would take my people. I'd have them complete the task more than once. Okay? They would complete the task listening to music, and then they would also complete the task not listening to music. I already know where you're at. Okay? And then what would my response variable be? Would it be the time for each of them? Or couldn't we say, Leva finished 10 minutes faster when she was listening to music?
You think they get better if they do it multiple times?
Yeah, absolutely. Let's talk about that. Which is where your men went right away, right? I could tell. Okay. It would absolutely happen that way. So what do we do? Let's go through. What were those 3 elements of that every good experiment has? Control, repeatability, replication, so large enough sample that we would expect the same results to happen every time. And one more. Random assignment. Have we randomly assigned anything? If I just everybody do before and then after. Okay, so when we do a match pairs design, it might be, I flip a coin, it comes up heads. So the first time you do it, you're listening to music. Flip a coin, it comes up heads, same. So you're going to start by listening to music. Flip a coin, it comes up tails. You're going to start with no music. So the order of the treatments gets randomly assigned. Is everybody with me? Now your music score and your no music score, you would expect about half, if you do a coin flip, or you can make it so that it's definitely one way or the other. Okay? Where you can have them evenly split. But by randomly assigning the order, both treatment groups have the same number of first time versus second time. Yeah?
Could you just let's say for the premium complaints, 20 additions and subtractions, could you just slightly change the numbers and
Yeah.
just not have to randomize it?
Yeah, but there's still a novelty versus not novelty thing would always be present, so you would still randomly choose the order of the treatments. Okay, so for a match pairs design, everyone completes the task twice. And we measure the difference for each of, we could say, music time minus no music time. So typically with a match pairs design, your response variable is no longer an individual number, but a difference between two matched numbers. What matches them together is that you are the ones doing it twice. And when you do a match pairs design, you create that lurking variable of order, like experience in doing the task, right? And you would want it to be the same task. So what you do is the order of the treatments is randomly assigned to each individual. Okay, now, some things that have happened in the past. I have had students who bomb a test because they were asked to describe how to assign treatments, and they described an entire experiment. Usually, that's better than the other way around, where I ask them to describe an experiment and they only describe assigning the treatments, not the other components of the controlling. What are you measuring? Those kinds of things. Okay. All right, so how do you decide which kind of design you want to do? Well, it depends, okay? So a completely randomized design is by far the easiest. You have your participants, you assign your treatments, and you're done, okay? It's way less work. Now, you are comfortable doing that when there's not a lot of uncontrolled variables. Like, when we were looking at that weight loss study, we had a lot of variables we couldn't control for. Height, age, etc. Okay? But in some studies, it's really easy to control for a lot of things, and so why go through the rigor of doing all of that other stuff if you don't have to? Okay? And it is a completely legitimate design. All right? Now, a block design is really useful if you have a lot of uncontrolled variables. That's when you would want to do this. Period. And you block by those uncontrolled variables to make sure that the treatment groups all have the same amount of them. Okay. Match pairs design is really good to do when possible, but it's definitely not always possible. Okay? It's great if you can do Okay, an example. Let's say they wanted to test a new antibiotic. Okay? Is it possible to do a match pairs test? And so maybe what do you guys think would be a good response variable to test a new antibiotic? How long you're sick, right? Essentially essentially recovery time would be, like, the idea is if we want to test that new antibiotic, the goal is that you get better faster, right? Okay? So let's say that I'm testing this for strep. Can you cure somebody from strep twice? Like, there's no way you could do a match pairs design when testing an antibiotic, because once somebody doesn't have the strep anymore, then they don't have the strep anymore. So you guys see what I'm saying? It's not always possible to do this match pairs design. It's great if you can, but it's not always possible. Every good? Do you guys feel like you have a good idea of like when you should do these things? Great. I got good news for those of you who won't be here tomorrow. Scope of inference is the last thing I want to talk through. In fact, this is the end of the notes packet, yeah? Or no?
Look at this page. I don't know what this is. Like says like design 1, 2, 3, 4.
Yeah, that's still scope of inference. Okay, so those of you who won't be here tomorrow, chances are I won't get to the different examples of each one's. I'll make a video of it, but I promise it won't be bad, okay? And I'll make a recording when I teach 4th period seniors. You will remind me to make said recording, okay? And then then I'll post that recording on Schoology for you guys. It'll be entitled Scope of Inference, okay? All right, so. Oh, did we do the tea tasting lady yet?
No.
Oh, man. Oh, man. Okay, those of you at home, pause the video and look at the link that says tea tasting lady. Oh, it was. Oh. Okay. All right, so that's annoying that it wasn't recording. Okay. And in the statistics world, it's a data-driven guess. Cool? All right. Now, something is significant if it is unlikely to happen by chance alone. Okay? All right, so as we said, Lady Adeline getting 8 out of 8 correct, that convinced us, yeah? And why was that convincing? I'm going to do this. It's unlikely that she guessed correctly that many times. Maybe we'll do smelling Parkinson's tomorrow. No, we can't do it tomorrow. There's not nowhere near enough time. Okay. So, remember, I'm going to go back to this even playing field, right? We're starting on an even playing field. Okay? And let's say we do our treatments and we see differences between our two groups. Okay? So if we see a small difference between those two groups, that could still be chance. That could be we did our best to make our groups even, but like our groups are never perfect, right? They kind of are like this. Right? So if at the end of an experiment we have them like this far apart, not significant. Because that could have happened just by the chance of how we assign people to the groups. If we see this big, wide difference between our two groups, that difference couldn't happen by chance of assignment. Okay? So when we see the difference that is not likely to have happened by chance alone, then we have significant results. And when we have those significant results, we can say the treatments caused the change, the differences between the groups. In other words, we can conclude cause and effect. Okay? So only in a well-designed experiment. It's well-designed if the treatments are randomly assigned. If the treatments are randomly assigned, we're assuming our groups are on par with each other. We randomly assign. So now, if there's a big difference, it has to be a difference that's big enough that we say not likely to have happened by chance. Okay? And later on this year, we'll talk about how we decide was our sample unlikely to have happened by chance. That's Unit 6. Okay? All right. So when we talk about the scope of inference, what we're really talking about is what can you conclude and about who. Okay? So when we talk about conclusions, we want to ask ourselves two questions. Is our sample representative? So, if that's the case, the selection of our participants is random. The other thing we want to know is, did we have randomly assigned treatments in a controlled experiment? If we have that, then we can conclude cause and effect. So there's two things going on when we talk about scope of inference. Who can we conclude about? And what can we conclude? So